Hello everyone, my name is Dubiel, and to begin this talk I would like to ask a simple question. When was the last time that you ran an application on production in JVM which was actually single-threaded? And it might sound like a simple question, but we use so many frameworks and abstractions that details like this sometimes slip our mind. Like, what are the threads? Where do they come from? How many of them are there in my application? Dijkstra once said that all those abstractions and frameworks, while they're very useful for us because they allow us on bringing business value quicker, faster, not having to worry about a lot of implementation details, they also are here to help us, and they should not make all the details which are underneath very vague. So, and what I see is that when we talk about threads, people tend to get very vague, like, there's some thread, there's something, but, this is something really low level and nobody cares about it. Well, I think we should, because only thanks to this, we'll be able to actually see the benefits that the frameworks give to us and actually control what and how they work and what they, the value they bring to our application. So, but before I start, a short context switch. My name is Dubiel, as I already said. I work at Allegro. I'm team leader in Skylab team. And my team is somewhere in between the infrastructure and business services. We have a lot of those business services. As you can see, it's almost like one microservice per person here in Allegro, which is sometimes crazy. But anyway, our goal is to provide common tools like PubSub or Spring Boot Starter to the other teams so that they don't have to do everything from scratch. And what comes in handy is the knowledge of how JVM and frameworks work. Okay, so let's start with the beginning, the Big Bang. We start with a new process on our virtual machine, on our machine. And it's like a Big Bang from the perspective of the threads. So in a very short amount of time, a lot of threads get created and they are ready to work. And then, after this time, we get to the stable state. Like, all the cluster, all the galaxies are there in place. Maybe from time to time, a supernova sparks somewhere, like a new thread being created just for a moment. But all in all, we're in a stable state. And to get from this abstract to something more concrete, I actually spawned a new application, simple Spring Boot application with HTTP server and MongoDB as a database, and graphed what threads are actually created at which time. So this is like 25 seconds of application lifespan. And you can see already like clusters of threads being created at certain periods. These are some kind of very specific events in the lifetime of our application. And just with the Big Bang, in the very beginning, a lot of things are happening. But then once we reach the stable state, there's not actually much. So what are those threads here? And how many are them? To better visualize this, I created another graph which shows how many threads are there in total in the application during different phases of the startup. And in this Big Bang event, in 0 moment, we almost instantaneously get almost 20 threads which do something. And then around 6 or 7 seconds, few more spawn, so we have 35 of them, something like this. And then there is a huge event around 25-second mark when we get another 100. So what happens and why? Why does it look like this? So first, the Big Bang, JVM starts. And the first threads that are born are actually certain VM threads. They come to life. It's around 20 of them. Then the Spring starts booting up. And while it boots up, it brings up the HTTP server, which creates its own threads. It also brings up the Mongo driver, which creates another set of threads. So those are here. And then, after 25 seconds, traffic starts flowing to the application. And this results in a huge burst of threads. Almost 80 of them are created. So in your typical JVM application, microservice or whatever, probably the traffic starts flowing immediately after Spring Boot context starts. I took a little break, added a little delay between those events just to be able to show them better on this map. But let's get back to the very beginning, the Big Bang, the process is born. What is a process? So in Linux, because the whole talk is going to revolve around Linux system, we have this concept of process tree. So whenever you start a Linux system, what you're going to get is this first process, which has PID number 1. It's the init. And in newer Ubuntu systems, it's systemd. And it's responsible for creating all the other threads. So we got this kind of a tree structure where each process has its own parent. And in this case, I've got some SSHD daemon working on this host, and I actually went there and created a new bash shell. So I just SSH there from my local computer, and this is my shell I'm operating in. So if I run Java version just to see what happens, well, what will happen is that in this tree, there's going to be a new child for my bash shell, and it's going to be this Java process. Okay? Of course, there might be a situation like this where systemd is responsible for creating this process by itself. Might happen as well. But what is the process? So the process is conceptually actually just a set of threads which can work on a shared memory. So they share the memory, they can read and write to the same places in the memory, and those are the threads that execute some code. So the process itself is just a collection of threads. Process doesn't do anything. Threads do things, but process is just an abstract name of this collection of threads and the memory they share. But, okay, this is how it looks in the system, but how does it relate to threads in JVM? What does it have to do with our machines, with our applications? So I use this command ps3 to show the processes tree, and what I omitted on purpose in previous slides is the next branch of this tree, and the next branch actually shows me that my Java process over here has some other children. Those are the threads. So in the curly braces are the threads. So PS3 is a system level tool, and using it, I can see threads in Java. So the only logical conclusion is that actually threads in JVM are native threads, are system threads. And this is how it actually works. So whenever JVM tries to create a new thread, what it does, it goes to the operating system and asks it, hey, can you create a new thread for me and give it to me? And then I'm going to run my code inside of it. And if you don't trust me, you can see it in the OpenJDK code. We actually call pthread_create function in there to create a new thread. So if JVM threads are system threads, it means that, first of all, they are observable using system tools, which will come in handy in a moment. And then the other thing is that it's not Java that is responsible for scheduling them. It's actually the system scheduler. So Java has no say in who runs where at what time. It's the system scheduler who does it. But let's get back to this observability. So there is this special place in Linux which is called prods. This is like a pseudo file system which contains information about running processes. And if you go there and go to this is the process ID, and to the directory which is called task, you're going to see all the threads which have been established, which have been created by this process. And this is actually the place where all the tools get their information from. So if it's in prods, if the information about threads is in prods, we can actually use PS to observe those threads, every single one of them. This is what the H flag does. So if we run PS with H flag and give the process ID of this process, we will be actually able to observe every thread from this application. Doesn't matter if it's Java or not. We can also do the same with top. Once again, the H flag. So, but let's get back to the PS for a moment, because what I actually did here is specified my own columns which should be shown. And there are two important columns here. One of them is PID. This is the process ID. And TID, which is thread ID. So thread ID and process ID, they actually share the same namespace. So as you could observe here, the number of process, the PID, and the thread IDs, they are actually in the same namespace. They're all integers. And if you start a process with, I don't know, ID number 100, there's a good chance that your first thread in this application is going to be 101, 102, and so on and so on. Yeah? So it's not continuous, but it's the same namespace. So it already shows that processes and threads are very close to each other. As I said, process is just a set of threads. So why is it so important? Well, let's say you have this kind of a situation. So you log on onto the host, and you can see that all the CPUs are actually on fire. So everything is utilized at 100%. How to be able, assuming that there is a JVM application working there, how to be able to quickly come up with what threads are actually causing all this mess? Well, by running this ps command I listed beforehand, we can see that you've got all the threads inside this application, and we can immediately see that there are 4 threads which are actually responsible for a lot of CPU time consumption. There are 4 of them, and we can also see their thread IDs. If only I were able to match JVM thread to the system thread. If only I were able to see the name of the thread which actually causes it, because the ID itself, well, it doesn't have too much information. Well, we can do this actually. It's pretty easy. So you know the tool which is called JStack. I hope you do. So JStack is what it does. It actually creates a stack dump from running JVM process, which means we get information about every single stack, about every single thread in this process, along with the stack trace and some other properties. And the interesting line for us is this one. So each thread is described with this line. And there are a few important properties in here, listed in here. So first of them is obviously the thread name. And this is what we would like to see. So the name of this thread here, it might not be the most descriptive one, but other threads might have more descriptive ones. And then we ourselves are able to actually name our threads the way we want them. Then the second one is TID, thread ID. It would be so cool if only this thread ID would be the same one from the system tools that I've shown you from PS. Actually, it's not. This thread ID, it's, first of all, it's hexadecimal, and then it's actually the pthreads ID. So it's the ID from this low-level library. It's not the thread ID as the system sees it. The thread ID as the system sees it, it's this other one, the NID, native ID. And it's the hexadecimal for thread ID as the one we could see in PS. So I know it gets a little blurry, so let's see it in action. Let's say I have this thread. It consumes 30% of my CPU time, and the thread ID is 8521. Okay, 8521. What I need to do is to first do a quick switch, so make a hexadecimal number out of it. So there are, when you Google it, you're just going to see a lot of pages that do it if you don't know how to do it by hand. And the hexadecimal representation is 2149. And then all I have to do is get a JStack and grab it with this number. And in this case, what I actually saw was that the thread with this thread ID 2139 in hex is a GC thread, yeah, from parallel GC. Well, this happens a lot. So it's really easy to actually match and use the system tools to match the JVM threads. And it gets even easier because what I've shown you was the code running on Java 8. And Java 8 and earlier versions, there is this method inside Linux implementation of threading code. And it says set native thread name. But unfortunately, it's not implemented yet. It was like this until Java 9. In Java 9, they actually went ahead and implemented it. And what it means is that whenever you use thread set thread name, the name that you set there is propagated to this operating system. The operating system becomes aware of it, of the name. Well, not all of it. It's only 15 chars, so there is a hard limit on the length. But anyway, it means that Java thread names become visible in system tools without any mix and match from JStack. And to see it in action, this is how the same application looks when it's run on JVM 10. And you can see that in the PS3, I have the names of the threads here. Well, only 15 first characters, but usually it might be enough for us. And the same for PS. So here, without even looking inside JStack, I can see that the two threads that actually use up my CPU time are GC threads. This is G1 GC because it's Java 10, so it's the default there. Okay, so great. We know which threads are actually eating up our resources without doing any more magic than necessary. As you could see on this graph, there are a lot of threads in the application. It's like 110 of them. And this is like a very moderate application. It actually doesn't spawn much of the threads. So why are we actually fixated on making making as little threads as possible? Because, well, if you've seen in Spring 5, we've got this new Webflux approach, when instead of programming in the old way, we start using Reactor, which creates a lot less threads, and everything is non-blocking, and everything is synchronous, and it's really hard to wrap your hand around it at the beginning. So why do we strive to get as little threads in our applications as possible? What is the cost of a thread? Well, for once, you have to allocate a stack memory for it. So a stack is like a private space for this thread to keep its own state, to keep some local variables. So whenever it's actually put into sleep, whenever it has to come up, we know the exact place and exact execution moment it should resume from. And this is the explicit cost. So we should be able to tell that it exists. There are also some implicit costs, especially in JVM. So one of them, it's not JVM only, but in general, is context switches. And then in JVM, each thread is a GC root, and there's you have to wait for it whenever you start a safe pointing, etc. But let's first concentrate on the thread stacks. So what's this? Where is this memory allocated, and why it's important to remember about it? So as you know, in JVM, we've got this heap, which is the memory which is governed by GC, and this is where most of our allocations happen, and there is a lot of magic going on there. And then there is all the other memory outside of the heap, which is sometimes called off heap. And this is the place where thread stacks live, because threads are system threads, so they have nothing to do with heap, with Java itself. They just come from the system. So it's natural that they actually live outside of this managed memory. And if you would like to see for yourself how much memory you need per each thread, what you can do is to use the tool called native memory tracking. It's built into JVM. And native memory tracking, this one here, what it does, it shows every single allocation done by this process. So whenever you go to the system and ask, hey, give me 10 kilobytes of memory, you're going to see it there. Yeah? So it doesn't track things that happen on the heap, but it tracks every single memory allocation. Okay, and this command here prints Java version, nothing more, only JVM version. This is the output, well, at least some of it. And what we can see is that to print JVM version, Java version, which is a bit sad, we spawned 18 threads. So this is number of threads spawned. And we actually took 18 megabytes of memory from the system. So very simple mathematics. 18,000 kilobytes, 18 threads, 1 megabyte per thread. Yeah. So, but should we trust it? Is it so simple? Okay, before I go into this. So the total, whenever we want to actually talk about how much memory our application needs, well, we tend to concentrate only on heap size. But it's not true. There's a lot of things out there of heap, and one of them is also thread stack sizes. So if you want to say how much memory you need, you also have to take into account how many threads are you actually spawning in your application and how big are their stack sizes. But is it this easy? How many threads can I actually spawn in an application? So let's say I have a host with some amount of RAM, and inside this RAM I have some portion of it is dedicated for heap, and there is all the other space. So let's say that I have host with 2 gigs of RAM and 500 megabytes of heap. Okay, actually this hurts my eyes. It has to be 512 megabytes. And then, well, let's say 300 megabytes for some other stuff, which would leave us with 1.2 gigabyte for threads, for thread stacks. So if I did my calculations properly, it would mean that I should be able to spawn no more than 1,200 threads. Yeah? Let's check it. So I have this kind of a box here, which actually which has 2 gigabytes of memory. Okay. And what I'm going to do is, I have the simple program which tries to spawn 5,000 threads. So if my calculations were correct, I should not be able to do this because it should hang at around 1,000. Let's try it. Well, it's way past 1,000. It's actually, well, it's around 5,000. It actually did it. How? Magic, yes. It's a kind of magic. Well, you cannot overflow your memory if the memory is not real. Think about it. So what happens here is that there are 2 kind of metrics by which you can measure the amount of memory you're using. And these are called virtual size and resident size. So virtual size, it's virtual memory size. It's not real. It's an address space that your process has access to. But unless you're actually going to do something with it, it doesn't have to be it doesn't have to exist in a physical world. Okay? And on the other end, there is the resident set size. And this is the memory actually used and allocated by your application. So this is like, whenever you want to see how much memory your application is consuming, you should go and check res, because it's going to show every single bit of memory that your process has allocated and is using. No matter if it's heap, off heap, whatever, it shows everything. So let's see how it works. I'm going to run this program once again. It's 5,000 threads. And I'm going to see the top for this. And what we can see is that it allocates almost 6 gigabytes of virtual memory, but this memory is not real. I mean, unless the threads are going to do something with their stacks, unless they're going to allocate something there, unless their stacks are going to grow, it doesn't have to exist. The real memory eaten up by this process is only 70 megabytes, nothing more. So this is a great thing because it makes it prevents our applications from wasting resources on the one hand, but on the other, it's a great peril because, well, if you're going to boot up your application in the morning when the traffic is really low, and it's going to create like 1,000 threads, and it's going to be okay because there is no traffic. And in the evening, whenever the traffic comes, well, people start clicking in your application, and then, well, you try to allocate this gigabyte of memory for this 1,000 threads. You might not have all of it. So it's not always so easy. So how many threads can I create then? Like, is there anything that would stop me from creating, I don't know, 100,000 threads on my machine? Well, there actually is, and those are called limits. And the one limit, which is particularly interesting for us, is the max user processes limit. And this is default value from Ubuntu, which is around 8,000 processes or threads. So we will be able to create not more. This user will be able to create not more than 8,000 processes. So if your application is really thread hungry, you should actually think about making it a lot more. But okay, then still, why less is more? Why we want to constrain the amount of threads that are there in our applications? Well, the other reason is that, well, we have the limited resources. So let's say we have a machine with only four CPUs. It's not an unusual thing to have a machine, virtual machine, for one microservice to have only 4 CPUs. This means that we are not able to do more than 4 things at a time. But then this demo application of mine already created like 100 of threads. So it's impossible for them to run all at the same time on those CPUs. So what are they doing? They're mostly waiting. Most of our applications are actually waiting for things to happen. They are not actively consuming CPUs. How great would it be? And while they're waiting, they are consuming resources. They have some stacks allocated, there are GC roots, etc., etc. So wouldn't it be great? And there is the other effect, which might be deadly, and it's called context switch. So to talk about context switch, we have to talk a bit about why our CPUs are so fast. So CPUs are fast because they cache a lot of things, and there are like in the standard architecture, there are 3 levels of cache: L1, L2, and L3 cache. L1 and L2 caches are exclusive for the core, and L3 is shared. Why are there 3 of them? Well, because it's actually very expensive to build big L1 caches. So L1 cache sizes are like measured in kilobytes, L2 megabytes, and L3 are like more megabytes. And what's really important is the access times to those caches. So L1 cache, it's really, really fast. It's like 1 nanosecond. You can go there and grab a value like this. L2 cache, 4 nanoseconds. L3 cache, 20 to 40, depends. And then RAM, like 100 nanoseconds. It's 2 orders of magnitude slower than the L1 cache itself. Okay? So let's say we have a thread running on this single core. The L1 cache is so okay. The amount of data that thread needs to run is called the working set. So working set is the data that it operates on. And L1 cache is so small that, well, you usually use all of it. So then most of it goes to L2 cache. And it's still a pretty good situation because L2 cache is really fast as well. So the data flows from L2 to L1. If you can constrain your working set to be able to put it in your L2 cache, you're in a great situation. Well, there might be some data cached for this thread in L3 cache as well. But what happens when another thread comes along? You know, we have 100 of threads inside our application, so they want to run at some point. So it goes there, and then all of the data we've been trying to keep so close to our execution point is useless. I mean, it's not necessary. It doesn't help us anymore because this is a new thread. It has its own working set. So what will happen, it will have to fetch all this data it needs to operate from the main memory, once again. And as you've seen, main memory, RAM, is really, really slow. Like it's 2 orders of magnitude slower than the L1 and L2 caches. So context switches, well, the context switch itself has some side effects, but they are not as deadly as the hidden context switch effects, which is actually like, you know, throwing away all the cache data. And you can assume that in a Java application, it can take up to 30 microseconds just to do the context switch between threads, if you count in the effect of throwing away all the data that you've been working on. And you can actually observe how many context switches are there in your system or in your process with tools like perf or vmstat. So we want to get here. Instead of having hundreds of threads, we actually try to have them like smaller number, I don't know, like 16 or 8 or something like this, a number which is really closer to the amount of CPUs we have, because only then, first of all, they will not waste resources by simply waiting, and secondly, they're going to be actively working all the time and trying to use the resources in the best way possible. And then we also mitigate the context switching effect. If we have less threads, it also might be possible for our system to use the thing called weak affinity. So the same thread might be scheduled on the same CPU instead of jumping between them. There are things and approaches which actually enable us to pin the thread to the specific CPU, but I'm not going to talk about this here. It's more advanced. But okay, let's get back to our application, the one which we started with. So this is the 25 seconds of its lifespan. The VM threads come to life, and let's zoom in on those VM threads. What's actually in this group, in this cluster of threads? So it all happens in first 100 milliseconds or so of the life of this application. And the first thing that actually shows up here is garbage collector. So the first threads that are actually created by the first thread in the application are G1 threads. And fun fact, the first thread in the application is called the primordial thread, like the primordial soup when every life, where the life started. So it's also here. Then we've got the VM thread following. VM thread is a specific thread because it's responsible for triggering JVM-wide actions. So whenever garbage collector wants to stop the world, it actually puts the task on the VM thread queue, and the VM thread is responsible for making everything stop, like the save pointing and everything. Then we have compiler threads, JIT threads, C1 and C2 threads, and then some other threads which are not so important for us. Okay, so this is like the first 100 milliseconds of our application lifespan. But then, these are interesting as well. So why is it so that the Spring context boots up and it only creates a handful of threads, and then only once the traffic starts flowing, we get all the other threads created? Why is it so? And to talk about it, we have to talk a bit about managing the threads themselves. So there are like two standard ways of creating threads. You can just go with the new thread, or you can be a better person and use the thread pools. So new thread, no, but executors are okay. And why is it important? Well, most of you probably would never use new thread in their code. Most of you probably know about the fixed thread pools, and they would use them instead. But it's important to know who we trust, and it's important to check the libraries that we use. Spring has this peculiar default. Whenever you use async REST template and do not configure it, or add async annotation and do not configure it, your code, your asynchronous code, is actually going to run in this simple async task executor. And what it does, it actually creates new thread per operation. So it's like a new thread. It has no upper limit for the threads it will create at the given time. So it's unbounded, unlimited. And then those threads are not reused. So it's not even a thread pool. They are not reused. So they're like, you just create them and then you throw them away. And we all know what Drake has to say about it. So he doesn't like it. I don't like it at all. So how is a thread pool built, and why should we use it? So a thread pool is a simple data structure which has slots for running threads. And let's say this thread pool is of 6, I guess, size? Yeah, 6. Whenever threads are busy, well, the thread is occupied. What happens when we have more tasks that we would like to run than the threads in our thread pool? What happens when it's full? Well, the thing that happens is that they are put in the queue. There is no exception here. I often hear that, well, exception is thrown. Well, no. There is a queue in front of a fixed thread pool. I'm talking about fixed thread pool here. And if there is a queue, there is another question. How big is the queue? Well, the sad thing about the standard library here is that this queue is unbounded in size. And, well, actually, it's integer.max value size. And if something is unbounded in size on our computers, it only means that it's going to grow for as long as there is enough memory and RAM. And where there is not enough memory, it's just going to be killed and just going to blow up. So we would probably like to constrain the size of this queue just for our own sake, so that it does not blow up our whole application. And the sad thing, once again, is that we cannot do this using the executor's factory. We have to dive a bit deeper and use the threadpool executor constructor. So the threadpool executor is the class which is the default implementation of all thread pools in JVM. And to construct it, you have to know a bit about the parameters. So there are the core pool size and max pool size, but they are not so important for us. You can just set them to the same value. This is what fixed thread pool does. But the one very important thing is the task queue itself. So we can pass on the implementation of the task queue which is going to be used. And we can put there, like, the queue of a size of 100 or 200. Well, monitor the size of it. Do a lot of things, because the default implementation here is just linked blocking queue. So it's unbound. It can grow to whatever size it likes. Okay, but it still does not explain why are those 80 plus threads created so late when the traffic starts flowing. Because all the thread pools I've been talking about, well, they should be created here. Like the Spring context is ready around here. And no new objects are created here. Like, there's no HTTP server booting up or something. HTTP server and JDBC and MongoDB connections are already available here. So why does it happen? Well, thread pools by default are lazy. So if you declare a thread pool of size 6, it actually will not start any thread. There will be 0 threads started. Whenever the first job comes, it's going to start 1 thread. Okay? If you're going to have 4 jobs there are going to be 4 threads running inside this thread pool, but not 6. Whenever the job is done, fortunately, the threads are reused, so they will not be killed. They are used. They will be reused and they are kept alive once their job is done, but it's not eager, so we will not create a lot of threads at the very beginning. We can force our thread pool to do this by using pre-start all core threads method, which will actually start all the threads as soon as the thread pool is ready. So what happened here is that even though the Spring context and HTTP server and everything was ready at the 7-second mark, the thread pools were of like 0 or 1 in size. Only once the traffic started flowing, the threads were created. And of course, creation of the thread is not instantaneous. It also takes some time. So in some applications, it might be actually advisable if you really care about warming up of your application to actually use this to force pre-starting of the cores in your application. And how was I actually able to get all this data about the threads which start in my application? Well, in Java 9, there was this neat but very barely known feature called unified logging. And it actually did a lot of cleanup to the logs in JVM. And you can get, at almost no cost, logs from creation of every single thread. You can create the same graph if you just turn this logging on for the thread and OS tags. So this is going to give you the information about every tag, about every thread which comes to life, and which dies. So you can also see how your thread circulate and which of them actually die. So the key takeaways, the things that I would like you to remember is that first of all, JVM threads are system threads. So you can observe them using system tools. I just shown you a few basic ones, but there are more there, like pitstat, etc., which can be very handy whenever you're on duty and something goes wrong in your application. We strive to get less threads because, well, less is more, because the negative effects of having a lot of threads are actually very that we can measure them, and they actually might have a huge effect on very CPU-intensive applications. And never forget about your thread pools, and remember that to always check the libraries that you use, because, well, even though they have been used by thousands of people, there still might be things that are not really quite good for you, especially when they are in the default modes. So that's it from me. If you would like to know more about me or work with me, there are the links, and I'm happy to take any questions you might have. Thank you.